roll tape. All right, we're going to finish up with our vapor power cycles. We started to look at those. Gosh, it was a while ago because I wanted to squeeze that in before our visit to the plant. And if you remember, the simple, straightforward vapor cycle that we looked at was just simply a heat being supplied by some means. Those possibilities are burning coal, oil. There's plants in Vermont that burn wood pellets. There are some plants that burn municipal refuse. Trouble with those, as you can imagine, is the exhaust gases and the like are the trouble. But that's, for the most part, immaterial to what our plant needs to do. Now, what we saw up in at Indec at their plant was what's called a combined cycle plant. Only difference with Indec's plant from what we'd already talked about is where this Q.H comes from. They have what's called a gas turbine topping cycle, where, and we'll look at this in next week. We'll look at air cycles, but essentially a gas turbine topping cycle pulls in air into a compressor where it's compressed and then run through a combustor where the fuel is burned. It, of course, expands greatly, gets a lot of heat, and then that's put through the gas turbine, and the result is a network out of the top cycle, and then this air that is still very, very hot. It's just not hot enough and energetic enough to really use for a gas turbine, but it's still got a lot of heat in it. So that is then run into the boiler, and that's where the Q.H comes from. That then runs the vapor power cycle, or supplies the heat to the vapor power cycle. So this is known as a combined cycle plant, because there's the Brayton cycle. You may have caught that term that Malcolm's dad and Mr. Miller used on our visit last Friday. That's the gas turbine cycle on the top, and then on the bottom, the Rankine cycle. Oh, dear me, I have to worry about my handwriting. Oh, now I'm all confused, all upset. We'll use nice block letters so there's nothing that can happen. No, you won't like that. I have to fix that. There we go. Okay, everybody. Everybody's a critic. That steam power cycle is known as a Rankine cycle, and the two together is known as a combined cycle. And then, so you can imagine a lot of stuff going on. The first thing we went into, when we went on the back of the plant and came in, you saw that big kind of louvered thing right outside the building. That was the air intake to the gas turbine compressor. And then we went in the building, walked up the little stairs into what was the gas turbine then. And if I remember, I understood that was the combustor and the gas turbine were both right there. And then that heat went on up to the boiler. And if you remember, the boiler for the vapor cycle looked like it was 2 or 3 stories tall. That's each one of these pieces is a huge piece of engineering going on there. You can make an entire career on any one of these things or you can be a cycle analyst yourself. And then there's other parts. The turbine blades themselves, there's people, that's what they do, is they work on turbine blades to make them more efficient. The cooling that had to go into them, and all those kinds of shape, every little bit of that, the metallurgy, all that stuff has to be designed. And so if you go into the power industry, there's a place for you there. So, I mean, they can find a place for Malcolm's dad. Anybody, right, Malcolm?
Didn't you say your PhD was in cooling of, what was it? But it was electrical.
Heat transfer and fluid mechanics is, what are your two favorite things in the world? Cold beer and a hot shower.
Holy shit, you're right.
What?
Oh, sorry, I just swore. I said, holy shnikes, you're right.
Sorry, Nana. She watches all my tapes.
Those are the best two things in the world. No, I said, what, your PhD was in cooling. You used
Yes,
cooling of,
but not power plants, not
It was,
microelectronics.
oh, microelectronics, sorry.
Yeah. All right, so a lot of time, effort, and money is spent on increasing the efficiency of these power plants. Even by little tiny twiddles of a percent, if you can catch a few tenths of a percent increase in efficiency, it can mean hundreds of thousands of dollars on a plant that size that we looked, or millions of dollars on other size plants. So the quest to increase the thermal efficiency, as well as the other efficiencies associated with the plant, is a big deal. A lot of money is spent on that. We looked at some of this. A lot of it is just, can you increase the area under the dome, or the area enclosed by the plant, enclosed by the cycle, without great increases in the Q inlet. Because remember that the area of a cycle is it's better on a PV diagram, but it's okay on a TS diagram for talking about isentropic processes. If we can increase that W net without increasing the Q net, actually it's not Q net, it's Q high, because that's the thermal cost we have to pay. Q low is an environmental cost, but not a thermal cost. So if we can increase the area on that cycle, a lot of times that can help. For example, can decrease the condenser pressure. There's troubles associated with that. Some, you don't want to operate too much under a vacuum because that can cause some troubles, but those kind of things can help. We looked, one thing you can do is what's done here, which is called the superheat. That's called the superheat horn. Just allowing the stuff to stay in the boiler a little bit longer. That will increase QH, but it will increase the net work by possibly even more. Plus, you can use a much more efficient turbine because you have a lot more vapor in the turbine than you do moisture. And then we looked at, real briefly, we looked at reheat, which is what the vapor cycle up at Corinth used, where they pulled some of the fluid out of the high pressure end of the turbine, sent it back into the boiler for reheat, and then put it into the low pressure turbine. Actually, it doesn't usually go that high, and then ran the cycle again from there. So both of those do include some increase in the heat required but it's enough of an increase in the work net that it makes the extra mechanics all worth it. So we looked at that. We did a reheat problem last week, and that's what the in-depth plant was using on the vapor cycle. And again, we'll look at the Brayton cycle next week when we finish things up. All right, so we're going to look at one other way to increase efficiency that's quite common, especially on a bit larger plants, and that's what's called regeneration. Regeneration. Okay. Should I go through this letter by letter and explain what those each are to you? Which ones are not perfectly formed, as if typeset? You know what I need to do? Start going to PowerPoint slides. Then you guys will be okay. And just sit over there, click through the whole class.
That before.
Huh?
We've all had that before with other professors.
Yeah. And that's why, because you ragged them to death till they finally gave up, took the easy route. But I'm fighting here because I got to at least keep doing this till I've gone through the other 74 and a half pieces of chalk that I bought. All right, so regeneration has a high pressure turbine, and partway through that turbine, the fluid is pulled out. Part of the fluid is pulled out, just a little bit of it. And that is then sent over to preheat what's going into the boiler. So that what goes into the boiler is already at a higher temperature. You don't need to add as much heat to it. So we have a couple things we need to pull together. So we pull a little bit of the flow out. So if we have say 100% of the plant flow is going into the turbine out of the boiler, we pull some fraction of that out here. Maybe we'll call it Y as the mass fraction. We'll put some numbers to this in a second. I just want to get you the idea. The rest of it continues through the plant and comes out. So this would be 100 minus Y as the amount of flow that goes through there. This then goes into the condenser. Now that's at very low pressure, whereas the fluid here that came out is at an intermediate pressure because it's taken out partway through the turbine. So this needs to be pressurized. Then the two are combined in what's called an open feed water heater. Just simply a large chamber, essentially, where they're mixed. The two streams are mixed together, so they have to be at the same pressure. They come out at the same pressure, but that's midway between the boiler and the condenser, so we need to have another pump that brings it up to the pressure of the boiler, and then they can be sent through the boiler at that pressure. All right, so that's the cycle we're going to look at today. We got a little bit to add to it before we get to it. Just the possible things we can do. Let me make sure I get my numbers right. That's not right. So 3, call that 4, 5 out of the low pressure pump into the open feed water heater. 6 and 7, and I think we'll do it. Yep. Now the open feed water heater works in a couple ways. One is it preheats the fluid so that the fluid going into the boiler is a little bit hotter than it would have been. Turns out that does increase the efficiency some. It's also a very simple contraption. You don't have to worry about pipes, you don't have to worry about corrosion as much. Another benefit of it is it can deaerate the flow, the water going through the plant by mixing it here with the steam that can take a lot of the air out of the fluid, and then that is a lot better for the boiler and the turbine because there's a lot less corrosion that way. So we have a 2-stage turbine here, and we now have 2 pumps that we need to power.
What's that? OFWH?
Open feed water heater. The other possibility, this requires that all 3 streams, the 2 streams coming in and the 1 stream coming out, are at the same pressure. Otherwise, they're not going to mix. There would be backflow. If they're not at the same pressure, you can use a closed feed water heater. And that's essentially the same thing, except that these 2 streams are separate from each other. And after the fluid goes into the turbine, into the feed water heater, it's either returned to the boiler for reheating, which is usually the case, or it can, sometimes it's just maybe used for building heat or something. So that might be something like this. 2 would come in out of the mid stage of the turbine. 5 would come up maybe from the first pump, and then the 2 streams are kept separate, and so this one would go around the different tubes, so that there's actually no mixing of those 2 streams, what's coming from 2 and 5, so they can be kept at separate pressures. But there's more complication because now you need a heat exchanger, which isn't quite as easy to produce as is an open feed water heater. So we'll look at an open feed water heater. Okay, most parts of it look pretty similar. We go into the turbine at a high pressure, high temperature. Then part way down, let me change where that's going to end up so it's more realistic to the numbers we're going to put to it in a second, so you don't get knocked off. So I'll put it maybe right about there. So that'll be 0.1. If it was an isentropic turbine, it might drop down here to about 0.2. That would actually be 0.2s at the same entropy. Some of the flow is taken out there to go across to the open feed water heater, and the rest of it is allowed to drop through the turbine. So pretty far in the dome, but it's just a cartoon sketch. So that might be 0.3s. more likely, in the numbers we're going to look at, there might be some irreversibility in the turbine, so there is a little bit less work produced in the turbine because of the irreversibilities. And then that's condensed back here to 0.4 at saturated liquid. Pumped up to 0.5, the intermediate pressure, where they're both combined to 0.6, and then both streams then are pumped up to 7, and that's the introduction into the boiler. So that would be P1, I guess. Okay. And this might continue down to whatever 0.3 is. Actually, that would be an actual inlet. It's so hard because I know I have to draw it perfect or everybody gets all over me.
So 3 is where? On your,
Here.
and 3S is?
3S, remember, is what an ideal turbine would do. But a real turbine is going to be back over here. So we have what would be turbine efficiencies that we have to look at. And that's where the actual power produced by the turbine is less than the work produced by an ideal turbine, an isentropic turbine. So far, all we've looked at are isentropic turbines. And so this would be m dot, well, whatever happens to be going through, well, any one of the stages doesn't matter. Because the m dots are just going to cancel, so all we need to look at is the enthalpy changes. So for example, for the high pressure stage, the real work produced would be H1 minus H2, and the ideal would be H1 minus H2S. And for real turbines, that turns out to be somewhere around the 80%, 85% region. In fact, what we'll use for this problem, when we put some numbers to it, is 85%, which means the turbine produces 85% of the work it could produce if it was indeed an ideal turbine, which means adiabatic, isentropic, irreversible turbine flow. Okay, so we'll put some numbers to this, and then you go to work. What the way we're going to do this turbine, or this split flow thing, is we'll use a definition of mass fraction. So all of the mass is flowing through one, but then part of it flows through there, and the rest must flow through there. Where instead of percentages, that's on a mass fraction basis. Where then Y is defined as the portion pulled out to flow through 2 compared to the total flow through the pant, which is how much flowing through state point 1. So I'll put some numbers to this. I want you to find what the mass fraction is and find the thermal efficiency of the plant. Okay, given a couple things. Net power, 100 megawatts. How much was the plant last week? At 130 megawatts, I think it was. So, you know what? That must mean they now have electricity in Corinth. Huh, that's awesome. That's awesome.
Used to use water wheels.
Well, however you get it, I don't really care. The boiler is at 8 megapascal pressure. The intermediate stage in the from the where the split flow is 0.7 megapascals. And then the condenser is at 0.008 megapascals. I think 8 and 0.008 are the same temperature or same pressure limits we had on our problem last week we did with reheat.
Wait, that's entering the condenser? It's coming to point
That is through the condenser. All the way across there is the condenser. Yeah, those are the same numbers we had on reheat. Temperature up here also 480 degrees. Both turbine efficiencies 85%. Assume both pumps are isentropic as drawn. If not, they'd tend to go over a little bit, take a little bit more power than an ideal pump. But if you remember, the pump flows are not all that all that great concern. We'll also assume that 0.4 is saturated liquid, as is 0.6. So that should be enough, unless I missed anything. I don't think I did. That should be enough for you to figure out the thermal efficiency and the mass flow rate. Sorry, we don't want the mass fraction. We want the total mass flow rate in the plant. So that'd be find m dot 1. And don't take this drawing too seriously of whether it points under the dome or not. You can determine each of those from the numbers as they are produced.
So there's enough mass flow from 0.5 from the low pressure side of that condensed water. There's enough mass flow of that to condense the high pressure steam coming in from 2.
Yes.
So that at 6, everything is condensed.
Flow at 5, which is relatively cold, the flow at 2 relatively hot, then it'll finish in between. So you can even put arrows on here if you want. There you go. Now everything's understandable. All right, so that should be enough for you to be able to answer each of those. You'll have to find, well, you know how much work is produced in the turbine. Well, you can get an idea how much work is produced in the turbine. You don't know how much is used for running the pumps. Oops, we better have a heat source. Or nothing's gonna run. Oh, by the way, these aren't perpetual motion machines. Yeah, what he meant was they'll run on their own without having to be started once you get them going. I didn't teach him thermos, so don't blame me. Okay, so that should give you the pieces you need. I'm not going to tell you anything more about how to do the feed water heater. I'm just let you work through that. You've got more than enough information and education to do the open feed water heater or the closed feed water. So that's your day today. So, anybody need tables? It's too bad that somebody stole my tables last week. It was Wednesday, didn't return them. Oh, who's not here today? Chris. Are you here, Chris? Who? Stole from me. So. Oh, you stole them?
No.
Bill, any of this look familiar?
Yeah.
Somebody needs tables? Nate's got his own. Good, prepared, well-prepared student. What time is it? Anybody else have another book? Oh, the word with that young man. When did you go to bed last night? Work the night shift at Hannaford? No?
Give me plenty of time to go to sleep too.
Phil, don't be a pest.
I'm trying to work. I go grab my calculator and there's this down here.
And then you say, excuse me, and get your calculator and go back to work.
See, but I can't because she doesn't do it in return.
So go sit over there.
Lost my pencil. Oh, I found it.
Okay, I'm here to consult. Remember, the actual placement of the points, especially these ones over to the very right of the dome, and that cartoon may or may not be quite right, so don't take it too seriously. And if you come up with those, this will be your get out of class question for the week. What?
6.4.
Everybody's wondering, what was the get out of class question that got you out for a whole week and sent you to Hawaii? What was that? How come only Bill answered that question?
And you were like, it's not true then. I'm like, it's not that dumb.
Only one of us got it ready.
I don't.
Trick question.
Does everybody have access to tables? If not, scooch over to someone and introduce yourself. It is the second to last week of the class. I will learn somebody's name now.
Yeah, I know, it's really flipping.
You okay?
Place to find that pressure.
Where?
We got 8.
Working? Along, okay. Good. Maybe I can find some
Looking for state part 1.
tables online that
I
would
use state
help.
part 3. Well, you use state part 1 first. That's easy. I'll start with that and see what you can do.
I know. I do the same one.
Yeah, you can get it once you get you get punched through state point 1, and it's consistent for 2s and 3s. And the pressure at 3s, consistent with the pressure at 3.
So you're saying this could be ideal H2S.
Find the entropy at point 1, and it's consistent with 2s and 3s.
All these.
And then you can use the entropy and the pressure to get your.
I would find those. I don't know, we have to find the variables that we need and then we can find.
Okay, there, I found some tables online. If somebody needs them, I can put them up there and I'll use whatever table you ask me to. Don't use R134.
It is easier. There's no way to find.
Got tables?
Table anyway.
Should be pretty much getting these tables memorized by now.
I have the English units memorized.
Got 'em?
I memorized the English units.
Well, let's just hope you get a job in America in a power plant. You're limiting yourself. You need to reach for the sky. You need to get on a big airplane and fly somewhere. Right, Bill?
Absolutely.
Got time for a trip again? You might as well. Who's going to graduation? Anybody? Besides me? You are? Okay, I already met your folks, but I'll meet them again.
What do we need?
Plus you get to see what I wore. I gotta see what you wore.
Over.
On Tuesday, you get to see what I wear at graduation.
That's our third one.
It's awesome. You can see me from the very farthest, highest seat. That's it? Just one person going to graduation? You and me will have a party. They do. Well, they have a buffet at the back. It's really good. So don't leave immediately. Go back there and schmooze with your favorite professors. Anybody stuck somewhere, not sure what to do?
Yeah, what do we do?
Okay, I take it you're speaking for the group. All right. Well, I want you to find efficiency. There it is. So at a minimum, well, that's not it. That's not the thermal efficiency. For the thermal efficiency, you're going to need the turbine work done, and you can find that from here, but you're going to have to do it for both turbines. Assume they're both 85% efficient. So you'll have to do that for both of those. Actually, that's not right. That's 3S there. Oh yeah, it really screwed you up. A bunch of babies.
Now it makes more sense.
What a bunch of babies. But you've got the power of the plant, the pumps. So that's both of the pumps. Assume they're isentropic. And then of course you got to find Q dot H. So you'll need the state points for the 3 state points for each turbine. You'll need the 2 state points for each pump. And you'll need 1 and 7 for Q dot H. Across the top. So that, I think that pretty much means you need all these date points.
Yeah, we want information from,
Just take S1,
You need
then you've got
H, you need the nth one.
Find T2,
We have P2.
and then find T2 using S1. And then you can find T3 using S2. Then you've got your temperature, pressure, your volume thing.
You use this and the isentropic ideal to actually find H2.
Ideal side, yeah, ideal gas, ideal turbine, or ideal cycle. That's just saying work for the ideal cycle.
It's not an ideal cycle.
No, you're comparing the actual work to the ideal work of a turbine.
Oh, yeah, for turbine. This is for turbines, not for cycles.
That's what I mean, I'm just
Yeah.
saying, it doesn't mean ideal gas.
No, as usual, especially when a liquid makes a terrible ideal gas. It's just a rule of thumb. So does that help you figure out what to do? You need basically H at every one of the points. For the high pressure turbine, low pressure, 2 pumps, and through the boiler. That's pretty much every H on the page. That's much more complicated, that one. You want to do that one instead? Look, you can see right inside the boiler.
what is that hat? What is that?
Exactly.
Just so it's not.
No, actually, big boilers and/or heat exchangers can be pretty impressive. If you like steampunk, you want to work for boilers, on boilers, not in.
Well, no, 0.9 is good.
As you go along, if you want to check some numbers with me, I'm happy to. Okay, Malcolm? What are you thinking? What are you thinking back there?
Yeah, that's one.
Because it's the H's that give the work for each one of these. For example, the work that needs to be supplied into point 1 depends on how much is flowing through there, which would be m dot 4. And the fact that you need to pump it up to here when it was down here. However, if you remember, H5 is not easy to spot, so we use the fact that H5 equals H4 plus V, V4, P5 minus P4. But you still need H4, and then the same kind of thing for the other points. Q dot H would equal m dot 1 times H1 minus H7. And so on. That's actually all that's left from an energy balance. Assuming steady state, no significant change in kinetic or potential energies at any of those components. Okay, Malcolm?
Still following a little bit.
You're looking at that and say, boy, I wish my dad ran that plan. That's an awesome plan. What? Dana's busy. Dana's getting all, Dana's had a long weekend getting stuff done. Still trying to copy from Dana as fast as he can. Get out of here quick enough to get back to Hawaii. Back in time for your test on Tuesday.
We're not be here. Oh, why? Yeah. I'm not coming back next time.
Okay. We're actually getting pretty used to not having you here. All the other professors on the hall were saying, my goodness, it was quiet last week. What, Phil?
Thinking if I stare at the board long enough,
It will. In half an hour, I'll put all the numbers up. If you remember, though, I don't think I'll tell you that. Because Phil wouldn't remember, he wasn't here.
Something to do with a Chinese guy?
Nope.
You have a good editor for your team.
Oh, Chinese. A good editor for my team?
Tape.
Oh. I understood what he said. I didn't like it, but I understood it. You, I didn't even understand it. Just not in the mood.
I'm trying, I'm trying.
Fresh piece of paper.
Want
It's
to
like-
check any numbers, anybody? Any H's or something
Yeah,
before
I
you
want to check
go?
yours. Can I check your numbers?
Yeah, I'll sell you this page. That's where I wrote down all mine.
Yeah.
Got any? Check them before you go. You don't. If you want to get the first one wrong and not get any more, none of the others are. Not happy. Let's get more and more complicated.
we're assuming.
Same numbers? No. Yes. Yeah. We're like you're drawing better just because it's kind of 3D. Look at that condenser. Which table? I better like you saturated. But
No, I did.
I found from my 8 o'clock class, if I make one little goof on a drawing, it's all I hear about the whole rest of the day.
Exactly.
So I think my drawing's so basic and simple, I can't even goof them yet.
I think it hits saturated by ready threshold.
So do we
Let's
still
see.
stay in the super table?
Because it shows up in the super heat table, but it's
That's not true. Ours, why is it on the calculator, guys? Oh, you have to AAA?
Yeah.
So. Obviously that's.
Yeah, well, you have to figure how far between here you are, so you'd be that far between
Same as yours.
that number, that's that, and that's that, and then that'll give you an intermediate one there, an intermediate one there. Then you interpolate between those based on where you are in the pressure.
Well, that's.
Was that the deal though, with those pressures? Didn't that happen to us last week?
It wasn't that, because it goes that high, it was just regular.
Well, that's how you do it, and you can do a kind of ballpark this, because some of these numbers don't have to be terribly precise.
Yeah, because then you can use H1 and H2S, and then you use that 55% ratio to find the real H2.
Yeah.
And you use the real H2 See what I
No.
mean?
Oh,
Yeah, it's like an overlap, you got an
No.
overlap your way through the
Because
whole
it's,
thing.
it's that big.
So all you do is, with S1, you find
H,
H2S.
2S has the same entropy,
Yeah.
because it's straight down on the TS diagram. And then you use the fact that H1 is fairly easy to find.
Okay.
Find the entropy there too, that will give you 0.2.
These temperatures.
Once you've got
themselves
0.2, you use 85% to find, once you find 2S, you use 85% and then you find H2.
H1 and H2S because I don't have.
No, H1 and H2S
How
aren't
do
the
you
same.
use-
Oh, it's S.
It's S that's the same, you take, you get S1,
Entropy,
then you use
well, I
S1
know
to
that the
find
entropy is the
H2S,
same for the
then
first
use
and second
H2S, find
ideal
H2.
state point.
Mhm.
And then
Then
how
use
do you
H2
use
to find
that,
H3S.
because it doesn't match up with
See what I mean?
what the tables would give you. I'm confused.
I got this.
What do you mean it doesn't match up with what the data is?
Yeah. Plug it in, you have to plug it in.
No, interpolate.
There's a 27.
Check it out.
That's different.
Estimate, how about that?
Yeah.
Check it
I
out,
just
Paul.
estimate.
I got this. I'll tell you exactly how to do it. Find S1. Use S1 to find H2S. Then use that formula at the top, the 85% there.
It's straight up.
You'll have H1 and H2S. Use that to find H2.
Yeah.
Then use H2 to find H3S. Then use H3S to find H3.
Yeah.
And that's it. And you just go around.
I guess it's the estimation that I don't feel
Work
comfortable.
your way around.
I don't like.
Well, here, then I'll find an online, somebody's got an online Steam property. Oh, here's one for the, here's one as
What
an
did you
app.
estimate
Nobody
for
has
this
this
one?
yet as an app?
6.63.
6.63, right?
Yeah.
Just so far off from the numbers they give.
Yeah.
It's just what, we'd say 60%, it's like 60% of the way. I just eyeball it. But
Yeah, you can eyeball.
Exactly. This is the mom at it.
Oh, that's useless. We're not paying $9.99 to the app store for that thing. I'll find this Inferno table here.
It's just point one, it's the outside.
That's
What is that?
it's actually lower than that.
We're at 27.62. Yes.
Done.
Plug that H2, take like 1.8 from off of the dish.
Okay, yeah. We just find this
That's
in.
sort of what I estimated. So
We're matching it.
yeah. That's what I was, or that's what I estimated.
Yeah, I estimated, yeah, 27.62.
Yeah, I saw that.
Thermopedia.com.
Well, that shouldn't stop, yeah. I know it all, it all, put up at 87.57.
It shouldn't be higher than shouldn't be higher than.
You should subtract it, don't add it.
It's already subtracted, like, take this, right?
Page one, and you multiply that times eight. And what you got left is 33. Oh, yes. Wait, no, we gotta flip it around.
Yeah, there's too much stuff.
This goes,
That's
from- yeah, all right, I subtract, I added 33.
Okay, God.
My bad. Sorry about that.
I'm trying to have a straight.
Turns out, you know.
Right, so, yeah, 2842 for you.
28. City that entropy.
Right.
Okay, there you go. You tell me what you wanna put in, I'll look it up for you. So the whining will at least decrease a little bit.
All right, P equals 0.00, P equals 8 kilopascals.
Okay?
And S equals 2843 kilojoules per kilogram per Kelvin.
Equals who?
2843.
That's, should be 8,000.
Or what is that? That's.
No, I mean 2,843. Sorry, I said 2843, I mean
That?
2843, yeah.
Kilojoules per kilogram.
Kelvin, yeah, which
Per
is the same.
Kelvin. Okay?
That's a huge estimate.
Yeah. But I'm just,
Am I missing?
I'm just putting things in here.
Should be an H. That's the H.
Yeah,
Oh, I'm sorry, that's
not
H, not S. H.
Goodness.
And what is this?
Yeah, what did I do here?
Well, why do you want H if you already have H? That doesn't make any sense.
Oops. Wait. What are you doing, Phil?
And what do you mean?
What?
Why do you want 8 kilopascals?
Yeah, we need.
Where's that?
We need, we're looking for S, not looking for 8, yeah.
Is this for point one?
No, we got H2. We need H2 to get H3S. But first we have to find S3S. So we need entropy, not enthalpy.
Okay. I'll just comment that out in case we ever need it again. S equals entropy, which sounds like santropy, which is a getaway place for people to go on vacation. Don't you think, Bill?
Yep.
Okay. Entropy,
Yes,
what?
P equals 8 and H equals 2843.
Okay. H equals, that's 20.
All right, 2850.
Close enough.
Yep,
So that's it?
that's it.
There you go.
Still, that's not. If you're looking for S2,
S3.
That's 3.
Okay, yeah. Well, S3S is what we're doing.
you mean,
We got it. Right.
is the pressure different? But you're looking all the way to the bottom.
Alright, so then we use that.
Now we use that to get the enthalpy.
Okay.
Oh yeah, we got the vehicle.
Yes.
Now this is what, 8 point whatever it was?
8.928. Yes.
Like that?
That's
Yeah.
it.
A little bit circular, but there you go. You, use this to find it, use H to find S, and then S to find H.
Yeah, there's something wrong.
No, it worked perfectly.
It's right, like put it down, write it down. Yeah.
Yeah, write it down.
Okay. All these are good.
If we
Go
have
back
any more
and-
thermos.
How did we get the first step
No,
right?
you used, we didn't use that to find H,
With
so you
your
use this
problem?
again.
Circles.
Oh yeah, we
It's
gotta
just
use
gonna-
that up there.
we
That's
have to
right.
leave that any
Oh yeah,
problem.
Except
yeah.
replace
We
one,
don't need
two,
the enthalpy.
three.
We don't need the H.
I guarantee
Yeah, that was
H
what
is
we
there.
did.
Well, I'll leave it there
It's
just
twice
in case you
before
do.
you go.
Call me back when you're ready.
I got it right here.
Any other helpful requests? Doesn't that give you confidence and ease and the ability to find properties?
Oh, okay. Oh, got it. I got it. We put in the wrong pressure. We were finding S. We're supposed to put in pressure at
Sure you can. Give it a try. See if your weekend starts early.
And then you can do the entropy to get the new H3. Alright, can I give you another number?
Sure.
Alright,
What do you want?
in the entropy part, the pressure is wrong. Yeah, you can-
Okay, comment that out. Pressure should be,
Should be 700.
That's what I was saying.
Yeah,
that's
okay.
kilopascals.
Paul was trying to-
Reading in kilopascals right now. So that's it?
Yeah, now we need to get on count that line.
Okay.
And now we'll get our S.
This is that.
Yeah, that's,
883. That's S2.
Okay. Now we can put that into the enthalpy thing and leave the pressure at 8.
6.883, okay. 6.883.
Yeah, and leave the pressure at 8. Nice, now we'll get H3. H3S.
H3S.
Yep.
Pretty close. What else? Anybody else want me to look up something so you don't have to interpolate? Steve? Yeah? Something?
No, I already got it. Jeez. You got the answer yet?
Figured out yet?
I didn't. I got it all right here.
Tomorrow?
Because now we know pressure, you can find that on the table. That's nice. Of course we can.
What else? Anything else? I'm here to serve.
We need H1. H156 should have.
Actually, we could just put S here.
So now for H4, you just do quality of 0 and pressure.
You need that?
Yes, we need.
Yes, you did.
Yes, we
Okay.
do.
I'll do whatever you want.
Yep, we need
It's
to get
pretty
another-
darn funny when we went in a circle.
Yes, that X equals 0 is the best because that's. an
S,
entropy.
S, do what?
Change
X,
that.
X equals 0.
What
That?
What do you want to add for me? Just like
You need
the
another
top,
pressure.
top one, change S equals S to X equals 0.
Pressure stays at 8.
It can, if I put S equals S, it'll use this S up in there and I'll have to retype it. So I'm getting tired.
Okay.
What pressure?
Pressure stays at 8.
Okay?
No. It should be underneath.
No, because the pressure is wrong for the S you're looking for.
I would just, fix the S equals S.
It feels sick of seeing that.
He's saying to change the S when you're going for enthalpy, put quality instead of S in there. Put a quality of 0.
Why? It's using this one. Oh, different pressure.
No, it's different
okay.
pressure, yeah.
That?
That should do it.
That's H4.
Yep.
Where's your actual CSE? Wait, pressure at 5 is
So it took me a whole nothing second. Taylor, how you doing? You on task? Are you on task? I mean, are you working on what you're supposed to be working on? Are you on task?
So really you have to find principles.
It is like fancy.
On 73 point? I don't know if it's.
No.
Oh, yeah. That's on it.
You gotta use S. You gotta find S.
Pardon me?
You gotta find S4.
What?
4S.
Nate.
What about
He
Nate?
would say this is not the same thing.
What did Nate do? Hey, they're talking.
I want you to type something.
Yep. What?
Entropy. Pressure.
Entropy.
Pressure 8. Quality 0.
Okay. Whatever you want.
What was S4? 5.
What do you need?
I've lost like all hope in trying to solve this problem. I
Wow,
have
where-
no idea.
Oh, you know what? We could just get, we can see
Well,
that on Kim.
Start here.
6.
Find H1,
Yeah.
We need H5.
then what?
But number two?
Well, no. When you have H1, get S12, S1 as well,
Right.
because that'll be this point.
Right.
That'll give you H2S.
Yeah.
That's very similar.
And then I
Once
found
you find H1 and H2S,
I found H2.
you can find H2. And once you find H2, you do exactly that same thing again.
Yeah.
To get which one is 0.3? But you need 3S to find 23. Using that.
So you assume the same. Yeah. You assume the 85% for the second one too.
Especially when I said both turbines are 85% efficient.
But we would need
I
temperature.
guess that's my
What?
confusion.
What?
We need temperature.
Same, they're both Ace Hardware turbines, steam turbines. And they guarantee 85% efficiency on all of their turbines for the life of the turbine,
No.
or the life of Burl, whichever comes first.
Doesn't change from 4 to 5. That's straight up. That's straight up, right? That line from 4 to 5 is supposed to be vertical.
Yes, I said take the pumps to be isentropic. If you remember, the actual pump work is very small compared to the turbine work, so isentropic, it's not worth figuring out isentropic in the pumps. Okay?
P is 700.
This is where that's.
You can actually take both.
Here, we'll do it this way.
700.
I'll have to change these numbers for you, okay?
Yep. Perfect.
That?
Yep. Awesome. So we got S6.
Got it?
No, it's gone, right? It's nice. We don't have H5 yet.
no unit problems.
Well, we might as well get that.
It's the small victories.
It's a huge victory. You guys treated it small. This is huge. I just prevented crashing the Mars lander. 'Cause I have no unit problem. How you doing? We'll check any numbers? No? Anybody else want to? Malcolm, got some numbers to check?
Oh,
Where you
I have
at?
a question. Where do lines of constant pressure change?
Uh,
On the left-hand side.
I assume the points they were looking at were either 0.4 or 0.6, because those are right on the edge of the dome, saturated liquid.
Where do the lines of constant pressure change on the left-hand side?
Where do they change? What's that mean?
Where does the line for 0.008 megapascals become the line for 0.7?
Oh. The line for 008 megapascals does that.
Okay.
This one does that up to there and across there. This one does that.
That's perfect.
That help?
Very much. Yes. Okay, we got another number for you.
Oh boy.
This is for H.
Uh-huh.
Pressure stays the same, except instead of an X value in H, and there's an S value of 1.99. Oh, sorry.
The S value from the one below?
No. It's gonna be, what? No, it's not it. Is it? No, it's not. It's.
Let's free, let's see. Is that it?
No,
Is that the S you wanted?
no. Wait. No, 0.5925, yeah. 0.5925. Five nine. Okay, there's H5.
I think we had that already.
No, no.
Okay, close.
Okay, so now we got another one. Pressure is 8 megapascals, 8,000. And S is 1.993.
Yeah?
Yep. And that's H7. Very well.
I am right.
Oh.
Okay. And what are you gonna do about the open feed water heater? Anything, you need to do anything with that? You do if you wanna find the mass flow rate, because you can find the Y, and then from that find the mass flow rate. So maybe we'll take a second to look at the open feed water heater. Out of board.
We're just gonna do some specific keys for that, right?
Nope, I wouldn't, because that's different phases with greatly different specific heats. So that's 2, that's 5, and that's what, 6. So don't need to do a mass balance, because that's what this is. We've already done a mass balance. But an energy balance would be whatever energy is coming in, M2H2 comes in one stream, M5H5 comes in the other, they combine and come out as 6. So there's the energy balance on the open feed water heater, simple as that. Energy just comes in, comes back out because it's running at steady state.
M6 is just 1.
Now, we can relate that to this because m.1 and m.6 are the same. So if we divide through by m.6, which is the same as dividing through by m.1, we can now get this in terms of y. And then once you get y, you can solve for the mass flow rates. So those cancel. m.2 over m.6 is the same as m.2 over m.1. So that is y. And this is, that's m.5 over m dot, which is 1 minus y. So then you can write y h2 plus 1 minus y h5 equals h6, and you can solve for y then. Once you solve for y, using that plus the net work, you can then figure out what the mass flow rate is. And you have 1 minute to finish. You lost still?
No.
No?
But
Good
now
enough.
I get it, that's all. Well, I don't have to.
You don't want to break a nail
Right.
or a sweat. Or you have what? You're thirsty? Well, I'm gonna have a great weekend. You guys are all staying. Maybe I'll, now, some of these you could have found pretty quickly because some of these numbers are exactly the same as last week's plant when we did reheat instead of regeneration. So some of these numbers we already had.